Thank you. First of all, I want to thank the organizers for the opportunity to give a talk. And this is a joint work with Charles Doran, Andrew Harder, Ludmil Katzarkov, and Victor Przyjalkowski. We also want to thank Jacob Lewis, who have contributed to this project at some point in the past. So, I want to start with the mirror symmetry for Fano varieties. And the rough idea of mirror symmetry for Fano varieties is that it corresponds to a Fano variety. It's a so-called Landau-Ginzburg model, which for us at the moment is just a quasi-projective variety, let's say Y, equipped with a rightarrow function on it such that its fibres should be mirror dual, whatever this means at this moment, to anticanonical sections of the Fano variety. But there are, of course, many different ways to make this precise. For example, from the point of homological mirror symmetry, a Fano variety should be considered as a local Abiyau pair X and anticanonical divisor on X, say V, which we will assume to be smooth. And it should correspond under mirror symmetry to a mirror local Abiyau pair, say ZD. And the act of compactification of the complement to V to X itself should correspond under mirror symmetry to equipping the complement to the divisor D with a proper function on Y. Proper here means just with compact fibers. From the point of Hodge theoretic mirror symmetry, on the one hand, we can consider a Fano variety as a symplectic manifold, and we can construct from its quantum cohomology. We can consider its quantum cohomology as a T module. On the other hand, we have a family defined by the function W, and we can look at the homology of its fibers. We have the Gauss-Manin connection, and we can build from it so-called Picard-Fuchs differential module. And Hodge theoretic mirror symmetry states that these two D modules are isomorphic after an appropriate regularization procedure on the symplectic side. So, from the point of toric mirror symmetry, if we have a Fano variety and we assume that it has some degeneration to a Fano toric variety, which is expected to be true for any smooth Fano variety, then the mirror of our Fano variety should admit open torus chart, which our potential map should be restricted as a Laurent polynomial. And the Newton polytope of this Laurent polynomial should be the anticanonical polytope of the this toric Fano variety, which arises degeneration for Fano variety. So one way to incorporate all of that is a theory of toric Landau-Ginzburg models. A toric Landau-Ginzburg model is a Laurent polynomial such that, first of all, its periods, I mean the periods of the family of hypersurfaces in the torus, which is defined by the Laurent polynomial itself, they should correspond to certain Gromov-Witten invariants of the Fano variety, so-called quantum periods. Secondly, the family itself should admit a relative compactification such that the total space of the compactification is a smooth Calabi-Yau variety, but non-compact. And thirdly, there should exist a toric degeneration of our Fano variety such that its fan polytope is precisely the Newton polytope of our original Laurent polynomial. And we will use a little abuse of notation. We would identify the Laurent polynomial or the family of hypersurfaces in the torus, which is defined by this Laurent polynomial, or with its compactification y. There is no harm there. So I also want to say a few words about Fano search project, which is in a way an inverse process. The rough idea is that by characterizing the Laurent polynomials, which appear as Landau-Ginzburg models of Fano variety, one should be able to recreate a family of Fano manifolds just starting from the data of Laurent polynomial and then applying some deformation theoretic techniques. And from that point of view, main challenge is to characterize which polynomials correspond to Fano varieties. And the current expectation is that toric Fano varieties, which we additionally assume to be Gorenstein, they should correspond to mutation classes of so-called rigid maximally mutable Laurent polynomial. But I do not want to give a strict definition. I do not need it. So let us return to Fano threefolds and let's recall a well-known result by Shakurov that a general anticanonical section of a Fano threefold is smooth, and it is not hard to check that in fact it is a K3 surface. And there is a well-known result of Baville that for a smooth Fano threefold and its a general anticanonical section, if we would consider the restriction map from the Fano threefolds to the anticanonical section, it should be an isomorphism. And moreover, the deformation space of pairs of Fano threefolds and its anticanonical section forms a complete family of K3 surfaces with lattice polarization by the Picaro lattice of the original Fano threefold. And it is known that toric Landau-Ginzburg models exist for smooth Fano threefolds, so it is a natural question of whether or not there exists, so to say, a mirror dual statement to Baville's theorem for toric Landau-Ginzburg models of our smooth Fano threefolds. Let me briefly remind a few words about mirror symmetry of lattice polarized K3 surfaces. First of all, we would call the lattice of three copies of standard hyperbolic plane plus two copies of negatively defined lattice E8 as the K3 lattice. And there is a standard result that for any complex surface S, its second integral cohomology as a lattice is isometric to the K3 lattice, but of course in a non-canonical way. And if we are given even lattice, we would say that some K3 surface S is polarized by L. If there exists a primitive embedding, a primitive means that its co-kernel does not contain torsion, whose image contains some ample class. And there is a relative version of this definition. We would say that the family of K3 surfaces is lattice polarized if we would consider the push forward of the constant shift on as And there should exist some trivial sublocal system which should induce lattice polarization by L on each fiber of the family. Great. So there is a theorem by Dolgachev that if we have a good lattice L, good here means that there exists unique up to isometry, of course, primitive embedding into the K3 lattice, then there exist coarse moduli spaces of L-polarized K3 surfaces. But of course, this condition to be good, to have a unique primitive embedding, there exist some sufficient conditions on lattice L in purely in lattice theoretic terms that would ensure that we have unique primitive embeddings. These are due to Nikulin. And in a general situation, the coarse moduli spaces of lattice polarized K3 surfaces has a finite number of irreducible components, and they are corresponding to equivalent classes of possible embeddings of our lattice into the K3 lattice. But in our case, everything should be okay. There would be no such thing, and the embedding is actually would exist and be unique. So let me say a few words about Dolgachev-Nikulin duality, also known as Dolgachev-Nikulin-Voisin duality, also known as mirror symmetry of lattice polarizations. It goes under many names. So let L be a primitive sublattice in our K3 lattice, and let us assume that its orthogonal complement should admit decomposition in the form H plus some new lattice L check. And then we would refer to L check as the Dolgachev-Nikulin dual lattice to L. Strictly speaking, the definition of a Dolgachev-Nikulin dual lattice implicitly depend on the choice of our H, and it has a certain mirror certain meaning from the point of mirror symmetry. I would comment on this a few minutes later. So Dolgachev-Nikulin duality is a form of mirror symmetry for lattice polarized K3 surfaces, and it is a corresponding on the level of moduli spaces of lattice polarized K3 surfaces. For some primitive sublattice, it should interchange complete families of L and L check polarized K3 surfaces. Complete here means that the corresponding period map is dominant. And informally speaking, Dolgachev-Nikulin duality interchanges algebraic and transcendental cycles on the K3 surfaces. And main result on Dolgachev-Nikulin duality is the following theorem by Dolgachev, that if we have complete families of lattice polarized K3 surfaces which are dual in that sense, then the dimension of the first families is precisely the Picard rank of a general member of the dual complete family. And combining it with result by Baville, we obtain that if we will look at smooth Fano threefold, if we would consider the moduli space of peak check polarized K3 surfaces, then its dimension is precisely the Picard rank of the Fano threefold itself. So the case of Picard rank 1 corresponds to modular curves. The case of rank 2 corresponds to modular surfaces, and so on. So let us introduce a bit stronger compactification assumption. Let's assume that we have our family of hypersurfaces in the torus, and we would call a compactification to a family over pi1, where its total space is smooth and the fiber over infinity is anticanonical. Then we would call such a compactification as local Abiyao compactification. It is known that toric Landau Ginzburg models for smooth Fano threefold admit such a compactification, and there is natural conjecture. So at the site of Fano threefolds, anticanonical sections of a Fano threefold are naturally polarized by its outer cycles, by the Picard lattice of the Fano threefold itself. So we would expect such a thing on the mirror side. So let F be a local Abiyao compactified toric Landau Ginzburg model, and F be its general fiber. Then we would hope that the Picard, then the dual lattice to the Picard lattice is precisely the image of the restriction of the second homology from the total space to a general fiber. But of course, we could ignore local Abiyao compactification at all and apply the Lynch theorem and just think of the right-hand side as the lattice of monodromy cycles, monodromy invariants. I'm sorry. So it is known that the conjecture holds for Fano threefolds of Picard rank 1, but unfortunately their approach does not generalize to the case of a higher Picard rank. So we have to introduce the following definition. So let X be a smooth Fano threefold of Picard rank greater than 1, and then we would call a toric Landau Ginzburg model of the Fano threefold, which was used in the paper of Chiltsov and Przyjalkowski on Katzarkov-Kontsevich-Pantev conjectures as a standard Landau Ginzburg mirror of X. And of course, such a definition would seem to be quite ad hoc, but in fact, it actually isn't, because if anticanonical class is not just ample but very ample, which is the majority of cases, then its standard Landau Ginzburg model is given by something called Minkowski polynomial. I do not want to give a strict definition, but it is a Laurent polynomial of dimension 3 with reflexive Newton polytope and a very special integral coefficients, which in some way correspond to decomposition of facets of Newton polytope into some elementary polygons. And the thing is that they are explicitly classified, and Minkowski polynomials with the same period sequence are connected by explicitly described birational transformation of the torus, which are called mutations. So we could choose any other Minkowski-Landau-Ginzburg model for X as well. And our first main result is that the conjecture actually holds for standard toric Landau-Ginzburg models. And moreover, in each case of Mori-Mukai classifications, we have explicitly constructed the dual lattice peak check. And then it is a natural question, what does happen with deformation theory of Landau-Ginzburg models? After all, Baveli result claims that the pairs of a smooth Fano threefold and its anticanonical section should form a complete family of K3 surfaces with lattice polarization by the Picard lattice. So let us introduce the following definition, which is after Katzarkov and Chepantev. We would call a triple of a smooth projective variety that a simple normal crossing divisor D and a morphism of Z2 pi 1 a proper tame compactified Landau-Ginzburg model if its fibre over infinity should be canonical divisor of the total space Z. And we would define the complement to the fibre over infinity as Y and denote by Y the restriction of our morphism F to the open part. And after all, it's almost the definition of local Abbe-Yau compactification, but it differs from the definition of local Abbe-Yau compactification by additional requirement of our divisor D to have simple normal crossings. On the one hand, in most of the known cases, that condition actually holds, and the fibers over infinity are simple normal crossing. But on the other hand, if, for example, we would look at some completely different classes of Calabi-Yau, I'm sorry, Fano varieties. So if we will look for Fano weight complete intersection, so that there is a result by Przyjalkowski that in general they have only singular local Abbe-Yau compactifications. So these two notions are potentially different, but in our case, everything should be fine. So our second result, which is partially after the result of Katzarkov, Kontsevich, and Pandev, is as follows. Let us suppose that we have a tame compactified Landau-Ginzburg models of dimension 3, and let us additionally assume that the pair of the total space Z and the divisor T is a local Abbe-Yau pair, which should additionally satisfy some certain minor topological assumptions. And let F be a smooth fiber of the corresponding morphism 2 pi 1. First of all, the forgetful map of the space of deformations of tame compactified Landau-Ginzburg model to the deformation space of Z itself is surjective, and as a consequence, the deformations of our variety Z are unobstructed, but it is actually after Katzarkov, Kontsevich, and Pantev. And secondly, the forgetful map to the space of deformations of a general fiber is submersion of relative dimension equal to the Hodge number 2,1 of that, and the subspace of the deformation space of the general fiber, preserving the polarization by the lattice of monodromy invariants. And as a consequence, if we would look at general deformation of our tame compactified Landau-Ginzburg model and on a general fiber of our morphism F, then its Picard lattice should be isomorphic to the lattice of monodromy invariants. So we have a naive version of Dolgachev-Nikulin duality. We have a Picard lattice of Fano threefolds or a Picard lattice of its anticanonical sections. And on the other hand, we have a Picard lattice of general fiber of Landau-Ginzburg model. But there is some subtlety here. We should deform the Landau-Ginzburg models itself. It is not true that if we would take a standard Landau-Ginzburg model, we would take its general fiber, and then its Picard lattice should be isomorphic to the lattice of monodromy invariants. Actually, the Picard rank of or a Picard rank of general fiber of non-deformed original standard Landau-Ginzburg model could jump. And we can think of that effect as follows. The Picard rank of K3 surface that varies in a family is controlled by the order of associated Picard-Fuchs equation, and for some cases it can drops down, and so we potentially have that the Picard rank could actually jump. So, but we could specialize that abstract result a little bit. Let us recall that if our smooth Fano threefold have a very ample anticanonical class, then it is given by a Minkowski polynomial, and we were able to specialize that deformation theoretic result to the case of Minkowski polynomials. Namely, let X be a smooth Fano threefold with a very ample anticanonical class, and let that df be its standard Landau-Ginzburg model after passing to tame compactification. And let us assume that everything is obtained at some point from the Laurent polynomial Cp. And the claim is that there is a family of Landau-Ginzburg models of dimension precisely the Picard rank of X, which is a deformation equivalent to our standard Landau-Ginzburg models in such a way that first of all, any small deformation of our total space is actually obtained by deforming just the Laurent polynomial itself. And secondly, that the deformation space of pairs of total space of compactified Landau Ginzburg models and its general fiber, they should form a complete family of big check polarized K3 surfaces. I would comment a little bit on the first part. There is a notion of a toric Landau Ginzburg model, not only for smooth Fano variety itself, but also there is a notion of a toric Landau Ginzburg model for a pair of smooth Fano variety X and some divisor on X. And they differ just by the period condition. We should replace the condition of main periods to be equal not to quantum periods, but to some other series of Gromov-Witten invariants corresponding to D. But in fact, it says that any small deformation of the compactified Landau Ginzburg models is in the end obtained by considering that toric Landau Ginzburg models for pairs of X and a divisor on X, and the choice of D is precisely correspond to the something of a dimension equal to the Picard rank of X. And for example, in our paper we have computed this toric Landau Ginzburg models for pairs for Fano threefolds of the form pi1 times Dolgachev surface with a very ample anticanonical sheaf. And let me say a few words about the implications for geometry of moduli spaces. Let us consider the natural projective compactification of our moduli spaces. M the Bailey-Barrel compactification, and it is obtained by adding some points which are traditionally called type 3 boundary components and some curves called type 2 boundary components. And it is well known that these boundary components could be described purely in lattice theoretic terms. Type 3 or respectively type 2 boundary components are in fact in a set theoretic bijection between the equivalent classes with respect to subgroup of orthogonal transformations of the orthogonal complement to L, which have spinor norm 1. And we should consider such equivalence classes of rank 1 or rank 2 totally isotropic sublattices of the orthogonal complement to our lattice L. But in fact, the existence of a type 3 boundary component implies that the orthogonal complement has a totally isotropic sublattice, but of rank 1. But from the point of view of Dolgachev-Nikulin mirror symmetry, there are more. There is just an embedding of the whole standard hyperbolic plane into the orthogonal complement. And let us give the following definition. Let's suppose that we have the projective line and some non-empty subset which is open in the risky topology. And we will consider, let's say that this subset is I don't know, it doesn't matter. And we would consider a rational local system over that open subset. And we would say that our local system is extremal if the first homology of the corresponding push forward to pi1 vanishes. And let's consider a map from the projective line to the barely compactified moduli spaces. And there is a finite number of possible variations of Hodge structure over the preimage of the original non-compactified moduli space, for which the period map should be equal to phi. And we would say that the map is extremal if one of these variations of Hodge structure has extremal underlying local system. It's a natural setting from the point of view of Landau-Ginzburg models, because a Landau-Ginzburg model, from our point of view, is not a family of K3 surfaces in a strict sense. For it could have some bad fibers, even reduced one. I'm sorry, reducible ones, but we could consider it as a map from pi1 to the compactified moduli space. And our third result is that we have a smooth Fano threefold with very ample anticanonical class. Then the moduli space of peak-check polarized K3 surfaces admits type 3 boundary points and explicit rulings, but extremal curves passing through these boundary points. But we should mention that the correspondence of Fano threefold X to lattice peak or peak check, it is not bijective. Some non-deformationally equivalent Fano threefolds could have isometric Picard lattices, so they should correspond to the same moduli space. But the thing is that different choice of such a possible X would lead to very different rulings on this moduli space. I guess this is it. Thank you.